Hey guys, let's dig into these homework questions. We're going to do 12 through 31, skipping around a little bit here and there. So number 12 says, a stack of 39 pennies is exactly as tall as a stack of 31 nickels. So interesting. Nickels must be a little bit thicker because we're saying these heights are the same. Do the two stacks have the same volume? So no, this has to be a larger volume because you're saying they're the same height, but this one's radius is bigger. Right? 13. Jacob is finding the volume of a cylinder. What did he do wrong? Okay, so how would we do this? Well, the area of the base times however high you'd stack that circle. Okay, so the base, I like that, right? Uh-oh, 2, where'd that 2 come from? Our height is 3. Cool. All right, 17. A plane intersects sections of equal areas in two solids. Are the volumes equal? No. So just because we cut the circle, that's the same. These circles I sketched are the same. This volume is a third of this volume. So let's say this is figure 1. This volume is a third of figure 1. Or you could say this is figure 2. This is 3 times figure 2. Cool. So this goes to the question of can we apply Cavalari's principle to different shapes? And the answer is no. We can't apply Cavalari's principle to different figures. Just because one cross-section, it has to be the same cross-section throughout. All right, we get 25. It says, Chiang makes gift boxes in the shape of right square pyramids. How sweet. So the bottom is a square 4x4. Boo! And it has an altitude of 4.5 inches. She fills each box with chocolate cubes with sides of cubes. Okay, that means every dimension, the base is 7/8, the width is 7/8, and the height is 7/8. A cube means all 3 sides are equal. Can she fill about 75% of the box? How many pieces can she fit in each box? Okay. So let's find the volume of each of these shapes like we've done in our others, right? So the volume of anything in the area is the area of the base times the height, but these are pointy, so we're going to divide by 3. The base is a square times the height, 4.5, divide by 3. So let's find this volume. Okay, so I get 20. Let me try that again. 4 times 4 times 4.5 divide by 3. I get 24. Okay. So the box is 24. Let's see what these little guys are. So I have 7 divided by 8 times 7 divided by 8 times 7 divided by 8. That's what they mean by 7/8 cubed. So 7 divided by 8 is a decimal. And then if I multiply it by itself 3 times in a row, Okay, I get 0.66992. Let me just double check that. Yeah, okay. Now we said, how do we compare the two? And they said they want to fit 75%, fill 75% of the box. So 75% of 24, and of means multiply. 0.75 times 24 is 18. Okay, so how many of these will fit in this 18? So we said we can divide the two. So we can take 18 and divide by the 0.66992 and see how many we get. 26.8. So not quite. So it looks like 26 candies will fit in the box and fill it just a little less than 75% of the way there. Cool. All right. A pile of snow looks relatively cone-like. Is plowed into a right cone. How many trucks with a capacity of 10 yards will be needed to move the pile? Okay, so let's figure out how big the pile is. This was our diameter, so we want to find the radius by dividing by 2, right? So half of 21 is 10.5. So our volume is the area of our base times the height divided by 3, because this is pointy cone, right? Okay, I get 1385.442 is my volume of my pile. And we're going to divide by 10 to figure out how many 10s would this fit. So divide by 10. That's how many truckloads. We get 138.5. So we're going to need a total of 139 truckloads to take this away. Neat. Okay, now looking at another kind of practice problem. 27 says our basin. Okay, so here's our cylindrical base. Our basin beneath a fountain is a right cone. Oh, this part is a cone. Okay, that's cool. The basin is a right cone with a diameter of 7. So we're not fooling, they're not fooling us. We're going to take a radius is half of that. So that would be 3.5. And it's 1 meter deep. So we got that. It says after the fountain is cleaned, the pool is refilled at a rate of, so this is a magical run, right? And we don't know if we have to multiply by 300 or divide by 300. So we're going to keep track of our labels. 1 cubic meter is, so that's another magical one. And we're going to keep track of that. We don't know if we have to divide by 1,000 or multiply by 1,000. We're going to keep track. So first we need our volume, right? So the area of our base is a circle times however high, divide by 3 because it's a cone. It's pointy. So 3.5 and 3.5, and our height is 1 meter, and we're going to divide by 3. So let's figure out what our volume is. Okay, so this is 12.828 meters cubed. Okay, so, but I want to get my answer in time. So that means I want meters cubed to go away. Well, it says here 1 meter cube is equal to 1,000 liter. So that's how I knew I wanted to multiply by 1,000 because I want to get rid of meters cubed. Now, as I continue to build, I don't want my answer in liters, I want it in time. So I'm going to actually divide by 300 liters in my magical one because, again, I want liters to go away. And 300 liters is equal to 1 minute. So this is 1 minute And I'm going to get my answer in minutes, which is what I want. So here, this is the same as just taking my numbers, this 12,828 times 1,000 and divide by 300. Okay, so we multiply by 1,000 and we divide by 300 and we get an answer. How long does it take? 42.76 minutes. So you could say about 43 minutes to fill up the fountain. That makes sense. I think it takes about that long to kind of top off my pool when it gets really, really low. So that's sounds like a reasonable amount of time. Mario makes candles in the shape of cones that are 12 inches tall. So here's our that's kind of an interesting candle, right? So there's our little wick. So there's our little flame there. Mario makes candles that are 12 inches tall. So that's our altitude, 12. And have a radius of 2 inches. Okay, thank you for giving us a radius. That makes it easier on us. He wants to use the same volume of wax to make candles that are 6 inches tall. Okay, so those will be able to do fatter. All right. What would be the radius of this? Okay, so we're going to solve for that. That'd be R. And then this would be, so we're saying we want these volumes to be the same. We can't use Cavalieri, but we can use just regular math, right? So the volume of the one on the left is the area of the base times the height divided by 3. So the radius is 2. Oh, here, this is pi. 2 times 2 times the height, 12, divided by 3. So that would be 16 pi. All right, now we need this one to be 16 pi because we want to use the same amount of wax. So we would have the volume is the area of the base, radius squared, times the height of 6 divided by 3 because it's pointing. And we want this to be equal to 16 pi as well. So using our Lynch swap, we want to get r squared by itself here and everything else. Move the 3 over here with the 16 pi. Move this pi down here. And move that 6 down there. So we end up getting radius squared is equal to 16 times 3 divided by 6. Interesting. So I get 8. So find the radius of the shorter and round to the nearest inch. So the square root of 8 would be my radius. So the 2.82. So round is to the nearest inch. I'm going to round up to 3 inches. 3 inches. So as predicted, it is squattier and wider. Nice. Number 30, it says, what is the volume of the largest cone that would fit in here? So if I look here, right, the base of this prism, it looks like a parallelogram, but we know it's a square. It's 8 by 8. So if I fit a cone in here, whoop, right, that would be my altitude. What's the largest cone? Well, notice this diameter would be 8, meaning the radius would have to be 4. So the volume would be pi r squared, h divided by 3. The radius would be 4. The height would still be 4, right? That should be the same dimension because it fits inside. And that gives us C. That ends up giving me 64 pi divided by 3. Well done. Okay, one more, right? 31. It says a designer is working on a design 2 goblets. Design A is based on a cylinder and B is on a cone. They want them to be the same height and width. Okay. So we know this volume is a third, or A is 3 times bigger. The client wants the smaller goblet to hold at least 100 fluid ounces. So B to hold greater than or equal to 10 fluid ounces. 1 fluid ounce is 1.8 inches cubed. Will design B be too large? Okay, so we need to find this volume, right? Volume is the area of our base times the height divided by 3. So that would be, if all the way across, then half the way would be 1.5. And our height is 6, and we divide by 3. So we get okay, I get 14.137. Okay, so we get 14.137 inches cubed. 14 by 137 inches cubed. But I want to move it into fluid ounces, so I have a magical 1. 1 fluid ounce is equivalent. So I'm going to divide by this 1.8 because I get 1 fluid ounce. So we can find out, right? See how this cancels here? So we're going to take our answer and divide by 1.8, and we get 7.85. So it doesn't, will it be large enough? No, not large enough. That is smaller than 10. Part B, the client wants the larger goblet to hold 20. Does designer A meet those requirements? Okay, so I don't really have to recalculate this because I know A is 3 times bigger. A is 3 times bigger than B. So I can just take my 3 times 7.85, which is still on my calculator, and I get 23.56. Does designer A, it wants it to hold exactly, the larger to hold 20? No, it holds 23.56.